Okay, here we are making a little video showing how you can find the integral of something that goes out to infinity. They're called improper integrals. All right. So in this case, even though x gets larger as we go to infinity, this gets way smaller. All right. Exponentials win in a battle with simple algebra like this. So to find the integral, you express it as a limit. This is supposed to be an n here. We're letting this variable n, so we can truncate this curve as it gets out towards infinity and it gets closer and closer and closer. We're going to have some n value there, and we're going to let the n value move out to infinity with our limit notation. And so we express the integral as going from 0 out to that truncation at n. And we just take the integral, and that's a little bit of fun, a little bit of review on how to do that, because we have to do it by parts. You'll see that we've got an algebraic expression and an exponential. So the Lie-8 rule, the algebra beats the exponential, so that comes last. So we let u equal x, du is dx. Then we set dv equal to the leftover bits, and we integrate that. We get what v is. We can pull out that negative 1/5, so when we subtract, there's the u and the v parts, minus, and then it's a minus 1/5, so it's plus 1/5, and then we get this little integral. And we can integrate that because it's not something that we need to use parts for. So here's the first part of that integral, and then there's the second part. So we've got the limit as n goes out to infinity of this integral from 0 to n. So when I sub in n, I now get this limit here, putting n in place of the x's. Have to be careful, forgot to do it there. And then this is the upper bound with the n's. This is the lower bounds where I'm plugging in the zeros. E to the 0 becomes 1, so this minus 1/25 is very important, but I'm subtracting that minus 25th. So I wind up with this first part here, this limit, then minus 0, this just goes to 0, and this is 0, and there's my 1/25th. So to evaluate this part, I have to use L'Hopital's rule. So we just take, and notice I've taken that negative 5n and I've just put it in the denominator with the 5. That gives us the form of this limit that's infinity over infinity, or minus infinity maybe over infinity. And this is going to, then through L'Hopital's rule, we can see that when we take the derivative of the numerator, it just goes to negative 1, and the denominator is unchanged, relatively speaking, so it's going to infinity, and negative 1 over infinity goes towards 0. So then everything drops out and becomes 0, and we get this answer of 1/25 there for that one. So that's very similar to one of your homework problems. The fact that we find a number there is proof that it is convergent. Okay. In doing this one, we have an integral that's going from negative 2 to 14, so we're not going out to infinity, but it's this integrand, the part that we're integrating, that is got problems. And the problem is that as we get negative 2 plugged in here, we're going to have 1 over 0, and that's a problem for us in math. So what we do is we think of it now as our n is sliding closer and closer and closer to this boundary, this asymptote, and I've got the integral still, so I have to do that integration. You can do this more or less by inspection. If you just notice that this is relatively simple, that's just the first degree, so when I take the derivative of this and then I go to take the derivative of the inside because of the chain rule, that just drops away and goes to 1. So if you just sort of try taking the derivative of x plus 2 to the 3/4, thinking of this as just like being x to the 1/4, how we would integrate that, make that 3/4. When I take away 1, I go down to the negative 1/4. That sticks it in the denominator and takes the 4th root of it. I've got this 3/4 here, so I just need to invert that so that when I bring the 3/4 out front, that'll cancel and drop out to 1. So this is the integral right here, and I'm taking it from n to 14, and I've got this limit as n gets closer and closer and closer to negative 2. From the plus side, that's very important. Evaluating that integral then, plugging in 14, I wind up with 8 because I get 14 plus 2 is 16. I can take the fourth root of 16, it's 2. 2 to the third power gives me 8. And then when I plug in n, because that's my lower bound, I get n plus 2, and I'm raising that to the 3/4 power. Well, if I do the limit of that, that's relatively easy. I can just plug in 2, negative 2 as I come at it from above. I don't have any division by zero problems. I can take the square root of a number that is positive, the fourth root anyway, and so that just goes to 0, and you wind up with this simple answer, again showing that it's convergent because that is a finite amount. All right, there we go.